Swayam Prabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 27. A brief recap, we were actually trying to look into the heat transfer across a mold phase. Given the temperature boundary condition of the mold phase, theta would be equal to the freezing temperature of the material, and then we would also assume that at x equal to infinity all the way from the mold phase, the room temperature conditions exist, that is theta equal to theta 0, which exists actually. So here we would like to discuss another numerical problem where we want to determine the solidification time of the following two cast iron pieces or iron castings when both are poured with no superheats. That means in this particular case the theta pouring and theta freezing are equal, there is no superheating as such of the material. So they are poured into sand molds, and the initial temperature of the sand mold or the room temperature could be about 28 degrees Celsius. So in two cases, one of the shapes that is being produced is a slab shaped casting 10 centimeter thick, the other was about 10 centimeter diameter sphere. So in both the cases there would be definitely different amount of heat transfer because of the geometry, and I think I had earlier mentioned about the geometry very clearly. So the data of the iron is given, theta freezing is that means freezing temperature or solidification temperature is 1540 degrees Celsius. This can be also the mold wall temperature, and then you have the latent heat of solidification is 272 kilojoule per kg. The density of the liquid metal is about 7850 kg per meter cube, and you know the density for on the specific heat capacity for the sand C 1.17 kilojoule per kg Kelvin. The K, the thermal conductivity of the sand, and the density of the sand has been given out to 0.8655 watt per meter Kelvin and 1600 kg per meter cube. So having said that, let us actually try to see how we will solve this problem. So let us do part 1 first. So let us assume L, B and H be the length, breadth and thickness of the slab. So in the slab casting case, that is how we have assumed this. Okay. So the volume of the cast is V equal to LBH, and the surface area of the casting is A equals twice LB plus BH plus LH. So we can assume that both the length and breadth of the casting are very high in comparison to the thickness, which is the case of a thin slab. Okay. And that is what we had illustrated earlier also. So this can actually be written down as twice LB, because wherever there are the H components they can be safely neglected. So hence the V by A in this particular case would be LBH by twice LB, that is H by 2, and in this particular case the height H or thickness H of the casting has been provided earlier to be 10 centimeters. So H by 2 becomes equal to 5 10 to the power of minus 2 meters, okay, 5 centimeters. So as the superheat level is 0, we have condition theta pouring equals theta freezing. Therefore L dash, which is equal to L plus rho m see theta pouring minus theta freezing, sorry, this is only Cm times, so there is no density term here, theta pouring minus theta freezing, it becomes equal to L as these two guys are same to each other. So, you have the value of L as twice 272 kilojoule per kg. Further, you have theta 0 equal to 28 degrees Celsius. So, therefore, we can write down both the coefficients lambda and beta. Lambda, as per the earlier derivation or proof, is theta f minus theta 0 divided by rho m L dash times of rho c. If you may remember, we had brought out two quantities beta and lambda and had correlated them with respect to each other as a function of the geometry. For the spherical case, it would have some relation; for the cylindrical thin cylinder case, it would have some other relation, so on and so forth. So, here we can write this down as 1540 minus 28 degrees Celsius times of density of the sand mold times of specific heat capacity of the sand mold, which is 1600 kg per meter cube times 1.17 10 to the power of 3 joule per kg Kelvin. Okay. So, that is how you find out rho and c, and this you have to divide by the density, that is density of the liquid metal. So, 7850 times of the L dash, which is actually in this case equal to L 272 times of 10 to the power of 3 joule per kg. Okay. So, that is how you arrive at the lambda value. Lambda is coming out to be 1.3252 in this particular case, and we also know further that the beta is estimated as twice lambda by root of pi, particularly in case of thin slabs. I think I had done this derivation or proof earlier how this relationship works out. And so, this can be written down as twice by root of 3.14 times of 1.325, and that becomes 1.4957. So, that is how beta coefficient can be calculated or correlated. Now, for the thin slab case, let us calculate what is the thermal diffusivity. K by rho c, where K is the conductivity across the mold, rho and c are the density of the mold and the specific heat capacity of the mold. K has been already given as 0.8655 watts per meter Kelvin divided by the density, which is 1600 kg per meter cube times of the specific heat capacity of the sand mold, which is 1.17 10 to the power of 3 joule per kg Kelvin. So, this comes out to be equal to 0.46 into 10 to the power of minus 6 meter square per second. Alpha Ts becomes equal to V by A square by square of beta as per the earlier expressions, and this V by A square is 5 10 to the power of minus 2 square, that is 25 10 to the power of minus 4 meter square divided by the square of beta, which is 1.4957 square. So, therefore, the value of Ts comes out to be 25 10 to the power of minus 4 divided by 1.4957 times of the value of the alpha, which has come out to be 0.46 10 to the power of minus 6 meter square per second, and this comes out to be equal to about 2430 seconds, approximately 0.67 hours. So, that is how much it will take, about close to 40 odd minutes for the casting to solidify as far as the thin castings case goes, in this particular case. We just do the same for the sphere. So, for sphere we already know the lambda value to be equal to 1.3256, and the relationship between beta and lambda is governed by the expression beta equal to lambda times of twice by root of pi plus an additional factor 1 by 3 beta here. So, we can actually substitute the values of lambda and pi and find out a expression for beta equals 1.4957 plus 0.4419 by beta. So, this brings us to a quadratic equation beta square minus 1.4957 beta minus of 0.4419 equals 0. If we take only the positive real root of this equation to find beta, then beta can be written down as minus b plus minus root over b square minus 4ac by 2a. Okay. So, calculating this, beta comes out to be equal to 1.75. Now, for a sphere of radius r equals 5 centimeters, the V by A really equals r by 3, obviously 4 by 3 pi r cube by 4 pi r square. Okay. So, r by 3, and this can be written down as 5 10 to the power of minus 2 by 3, because the radius is 5 centimeters. So, alpha ts in this particular case would be V by A square by square of beta, and this becomes equal to 25 by 9 times of 10 to the power of minus 4 divided by square of beta is 3.05 is borrowed from the solution of beta here, or the Ts value comes out to be equal to 198 seconds or 0.055 hours. So, you can think about the reduction in the case from thin slab to sphere in the Ts values, time of solidification values. So, that is how we basically try to arrive at solutions regarding Ts or solidification time of the casting based on geometry. We still need to develop 2 more cases where we would like to illustrate particularly the concept of thermal resistance and thermal capacitance. So, for that I would just urge you to look into this electrical analogy of all thermal problems, where there is a mass m of specific heat capacity C, and there is a heat input from one side and output from the other, and there is a temperature gradient which exists delta T across this mass. So, we all know that the total amount of heat transferred would be equal to mc delta T, and mc is basically called the heat capacitance, because this can be an analogy between a capacitor. So, in a capacitor, if you have a charge q flowing and capacitance is C, you could have q equal to Cv relationship between the charge and the voltage. Here the heat is the charge flow, it is the analogy for charge flow, and the voltage here the capacitance is having an analogy delta T, which is the driving factor or the potential for the heat to flow. So, obviously there has to be a temperature gradient, this side has to have a higher temperature and this to a lower temperature for the heat to move from the high temperature to the low temperature. So, this is the gradient, just like voltage gradient which carries forward charges in electrical circuit. So, having said that, mc therefore is basically the capacitor equivalent, C equivalent in the thermal circuit. So, in our future analogies we may be needing to use this electrical analogy for understanding what is the thermal capacitance or heat capacitance. Similarly, we have the thermal resistance analogy, where if we use the one dimensional Fourier's law, the q dot or the del q by del T, the rate of heat flow across this mass, would be related to the temperature gradient delta T by x, where x is the length across which this delta T temperature gradient exists, and it will be proportional to this temperature gradient, and the proportionality constant here is the thermal conductivity times area. So, there is a very famous Fourier's law of heat conduction, one dimensional heat conduction. So, I would like to just draw an analogy here between a resistor which is having a current I, across the resistor is a potential V, because of which the current is formulated. So, I, which is actually the rate of charge flow, same to rate of heat flow here, becomes V by R. That means whatever is the potential divided by the R. So, in this particular case, the heat resistance comes out to be equal to R equals x by Ka. Okay. So, this is V, this is the analogy, and this x by Ka becomes the resistance R. Okay. So, that is how we get the thermal resistance. So, therefore, just as the electrical circuit, there is a there is a potential drop, there is also going to be a temperature drop as the heat front meets new material or additional material. So, just for the sake of analogy, please keep this in mind. We will close this module here, but in the next module we will like to do again a different variation of the problem by seeing what is going to be the boundary change if supposing there is an issue of the liquid not spreading across the whole surface. Okay. And so, there is an air film which is formulated between the solid boundary of the metal and the sand boundary. Okay. So, with this we would like to end. Thank you.